All right, everyone, welcome. Let's get right into our deep dive on synchronization. You've got your final exam coming up, and my goal here is to make sure you're ready. We're going to cut through all the dense theory and focus on exactly what you need to know, the core concepts, the real-world implementations, and the APIs that you'll absolutely be tested on. Let's do this.
So here's our plan of attack. We'll kick things off with those classic sync problems. They're the foundation. Then we'll look at how the big players, Windows and Linux, handle this stuff in the kernel. From there, we'll jump into the code you'll actually write, looking at the POSIX and Java APIs. We'll even touch on some newer alternative approaches before we wrap it all up with a quick hitter review for the exam. Sound good? Let's go.
Okay, first up, let's tackle the classic synchronization problems. You should really think of these as the ultimate proving grounds, you know? They're like the stress tests or the battlegrounds for any new concurrency tool. If a new lock or a new semaphore can't handle these problems cleanly, well, it's probably not going to be very useful in the real world.
So we'll start with a big one, the bounded buffer problem. You'll probably hear it called the producer-consumer problem, and honestly, it's the absolute classic coordination challenge. I mean, think about it. You've got one thread, the producer, putting stuff into a shared buffer, and another thread, the consumer, taking stuff out. The question is, how do you stop the producer from trying to cram an item into a buffer that's already full? And on the flip side, how do you stop the consumer from trying to pull from a buffer that's empty? It gets even trickier because these two threads could be running at totally different speeds.
Okay, now this is a slide you're going to want to pay close attention to for your exam. This is the classic semaphore solution. We've got three of them working together. Full counts the items in the buffer, empty counts the open slots, and mutex is our gatekeeper. It makes sure only one thread is messing with the buffer at a time. Simple enough, right? But here's the absolute most critical part, the thing that will almost certainly be a question, the order of the wait calls. The producer has to call wait empty before it calls wait mutex. Why? Just think it through. What if it did it the other way? It would grab the lock, then check if there's space. If the buffer's full, it has to wait, but it's still holding the lock. The consumer can't get in to free up space. That's deadlock. So that order, wait empty, then wait mutex, isn't just a suggestion, it is the entire key to making this solution work.
All right, next up is the readers-writers problem, and this one is everywhere in the real world. The flight reservation system is a perfect example. You can have hundreds of people looking at flight availability at the same time, right? That's fine. But the second someone goes to book a seat, that operation needs exclusive access. You can't have two people booking the same seat at the same time. So the challenge here is balancing these two needs, allowing as many readers as possible to access the data concurrently while making sure any writer gets exclusive, uninterrupted access.
So how do we pull this off? Well, here's a pretty common solution. We've got two semaphores and a little counter, read count. The RW mutex semaphore is the big one. It's what a writer has to grab to get exclusive access. But for readers, it's a bit more clever. The very first reader that shows up is responsible for locking that RW mutex. After that, as long as that lock is held, other readers can just waltz right in. They just increment the read count. Then, when the very last reader is done, it's their job to unlock RW mutex so a writer can finally get its turn. That other semaphore, mutex, is just there to protect the read count variable itself, to prevent a race condition while readers are coming and going. Now, there's a huge gotcha with this specific solution, and it's a classic exam topic, writer starvation. If you have a constant stream of readers, a writer might wait forever. Keep that in mind. And that brings us to our final classic problem, the one with the best name, the dining philosophers. Yeah, it sounds a little silly, but it's actually a fantastic stripped-down model for a really complex and common problem. It's all about how you allocate multiple resources to multiple competing processes. In this case, each philosopher is a process, and they need two resources, the chopsticks, to do their job, which is eating. Get this wrong, and your whole system can just stop.
And this right here shows you exactly how things can go horribly wrong. The simplest, most obvious solution seems to be, hey, let's just make each chopstick a semaphore. A philosopher tries to grab their left chopstick, then their right one. Easy, right? Well, what happens if all five of them decide to eat at the exact same time? They all sit down, they all successfully grab the chopstick to their left, and then they're all stuck. Every single one is waiting for the chopstick on their right, which is being held by their neighbor, who is also waiting. Nobody can move. That, my friends, is a perfect textbook example of deadlock.
So how do we fix this? A much safer way is to use a monitor. And the core idea of the monitor solution is totally different. A philosopher isn't allowed to pick up any chopsticks unless both of them are free. It's an all-or-nothing deal. So when a philosopher gets hungry, they call a pickup function. Inside that function, we test if both neighbors are eating. If the coast is clear, fantastic. They grab both chopsticks and start eating. But if not, and this is the key, they call wait. And the magic of a monitor is that when you call wait, you automatically release the monitor's lock. This lets someone else, maybe a neighbor who is just finishing up, come in and put their chopsticks down. It's that atomicity, the ability to check for and grab both resources in one single uninterruptible operation, that saves us from deadlock.
All right, so that's the theory. We've got the classic problems down. But now let's get into the real world. How do major operating systems like Windows and Linux actually give us the tools to solve these kinds of problems in the kernel? When you look at them side by side, you can see they have pretty different philosophies. Windows kind of wraps everything up nicely in something called dispatcher objects. Think of these objects as having a little traffic light on them. If it's green, or signaled, a thread can go. If it's red, non-signaled, the thread has to stop and wait. Linux, on the other hand, gives you more of a raw toolkit. You get everything from super fast atomic integers, which are great for simple counters, all the way up to heavyweight mutexes and semaphores for protecting those really complex chunks of code. Okay, now this is a really cool and clever detail about how the Linux kernel works. It's all about how it handles spin locks. On a system with multiple cores, a spin lock does exactly what it sounds like. A thread literally sits there and spins in a loop, burning CPU cycles, just waiting for the lock to become free. But what about on a system with only one processor? Spinning would be completely useless, right? The thread that holds the lock can't run to release it if you're busy spinning, so Linux does something much smarter. On a single-core system, trying to acquire a spin lock doesn't spin at all. It just temporarily disables kernel preemption. That means the operating system can't switch away from the current thread. As soon as the lock is released, preemption gets turned back on. It's such an elegant and efficient optimization. Okay, let's shift gears again. We've gone from theory to the kernel. Now let's get to the part you'll be typing into your editor, the APIs. We'll start with the C and C++ world. If you're on any Unix-like system, and that includes Linux and macOS, the standard you're going to live by is POSIX, specifically the pthreads library. Now, for your exam, you just flat out need to memorize these function names. If you need a simple lock, what do you use? pthread mutex lock and pthread mutex unlock. Easy. Need a semaphore? You've got semwait to wait or decrement, and sempost to signal or increment. And for those more complicated situations where one thread needs to wait for a specific condition, you've got condition variables. One thread calls pthread cond wait to go to sleep, and another calls pthread cond signal to wake it up. And please remember this. You always use a condition variable with a mutex. They're a package deal. All right, let's switch languages now and head over to Java. Java is interesting because synchronization has been baked right into the language from day one. But the modern Java concurrency library gives you a ton more power and control than the old school stuff. In Java, you've basically got two main ways to handle locking, and knowing the difference is key. First, there's the synchronized P word. This is the simple, built-in way. You just slap the word synchronized on a method or a block of code, and the Java virtual machine takes care of all the locking and unlocking behind the scenes. It's basically a monitor built right in. Then you have the more advanced option, reentrant lock. This is an actual class, not a keyword, so you have to do the work yourself. You have to explicitly call lock and unlock. So why bother? Well, in exchange for that extra typing, you get a lot more features, like fairness options, and, most importantly, the ability to create multiple condition variables from a single lock, which is a total game changer for some of the more complex problems. And if you're going to use reentrant lock, this pattern here is not a suggestion, it is a rule. It's non-negotiable. You must, always, without fail, put your unlock call in a finally block. Let me say that again. Unlocking call goes in the finally block. Why? Think about what happens if some code inside your try block throws an exception. If the unlocking call wasn't in a finally block, it would never get called. You'd have a lock that is held forever, and your program would grind to a halt. This is probably one of the most common and most dangerous bugs you can write in concurrent Java code, so burn this pattern into your brain. Okay, so up to this point, our whole world has revolved around one thing: locks. But let's be honest, locks are tricky. It's way too easy to mess them up and create deadlocks. They can hurt performance, and they just make your code harder to reason about. All of these headaches have really pushed a lot of smart people to ask, is there a better way? And that leads us right to this really fundamental question. Are locks really the only answer? What if we could just get rid of them? What if we could write concurrent code that was safe by its very design, without ever having to manually acquire or release a lock?
One really cool answer to that question is something called transactional memory. And the idea is actually borrowed straight from the world of databases. Instead of locks, you just mark a chunk of your code as being a transaction. The system then optimistically tries to run it. If it gets to the end and no other thread has touched the same data, great, the changes are made permanent or committed. But if some other thread did interfere, no problem. The system just throws away all the changes from that attempt. It rolls back and then tries the whole thing again. You, the programmer, don't write a single lock. It just works. This can be done purely in software, which we call STM, or, and this is much faster, it can be built right into the CPU hardware, which is called HTM. But there's an even more radical approach, and that's to just change the fundamental rules of how we write programs. This is the core idea behind functional programming. In a purely functional style, data is immutable. That means once you assign a value to a variable, it can never, ever change. You don't modify data, you create new data. And if you think about it, if data can't be changed, then what's the problem? There's no such thing as a shared mutable state to protect. Race conditions, by definition, become impossible. You've eliminated the entire problem class just by changing the rules of the game.
All right, we've covered a lot of ground. Let's wrap this up and bring it all home with a super quick, rapid-fire review of the stuff you absolutely positively have to know for the exam.
Okay, let's nail this down. 1. The classic problems, bounded buffer, readers, writers, dining philosophers. They're your theoretical proving grounds. 2. Operating systems. Windows uses those dispatcher objects. Linux gives you a fine-grained toolkit, from atomic ops up to mutexes. 3. APIs. For POSIX, you need to know the pthread mutex, sem, and pthreadcon family of functions. For Java, it's all about the difference between the easy synchronized keyword and the powerful reentrant lock class. And 4. Remember the alternatives. Things like transactional memory and functional programming are designed to get you away from the whole mess of manual locking. Got it?
So I'll leave you with one final thought to chew on. We're moving into a world where every single computer, even your phone, has multiple cores. Desktops and servers have dozens, even hundreds. In that world, is our old way of thinking, using locks that force threads to stop and wait, going to become the biggest bottleneck we face? Is the next truly essential skill for every single developer going to be mastering these lock-free approaches? Something to think about. All right, that's it for our review. Go crush that exam. Good luck.